Okay. So we're gonna pick up the slide number 15. So we left off last week with being able to write chemical formulas. Chemical formulas is not something big and scary. All we mean by chemical formula is you have the elements and you have that little subscript. The subscript tells you, The subscript tells you how many of that element you're gonna need. And remember, that number is set and it has to stay that number, or else it changes what you're dealing with. So for example, if you have water, which is H2O, that's kind of the go-to formula because we're all familiar with that, right? Capital H, little 2, big O. Yes, can you picture that in your mind? Sure. I think so. So that's a chemical formula. If we would change the subscript and make it H2O2, instead of having basically that 1 for oxygen, we make that 2, that becomes hydrogen peroxide. That is definitely not the same thing as water. So those subscripts are super important. And we get those from the opposite element's ionic charge, right? So when we have the charges identified and then we crisscross them, that gives us the subscript. And we showed through that one little video with the arm and link video why we get those numbers. It's not just random, okay? So that's just kind of catching us up for where we were last week. Remember, in Google Classroom, those sites, those practice sites are there for you if you want to get a little bit more practice with chemical formula writing, okay? So this slide is basically just showing, hey, these charges that we get from the valence groups are super important. The meter stick. All right, so there's really nothing for you to fill in on that one, just kind of reinforcing the idea that those ionic charges are kind of where we get our subscripts from. And they're all based on those valence electrons. So I want to back up for 1 second. I think I forgot to, oh man, I went way too far. I think I forgot to click on the last, this would have been on slide 14. Did you guys have that? For some reason I thought I clicked, yeah, it was like in the afternoon I realized when I clicked that there was a second click and I just left it on this one for you guys. So this is slide 14. You should have had this first bullet, but then there was a second bit of information that was important. Because you're dealing with the ions, and obviously the ions are charged, that's what makes them an ion. But when they come together, the compound itself becomes neutral. So sodium is positively charged, that cation. Chlorine is negatively charged, the anion. When you put sodium and chlorine together, that whole compound of table salt, that NaCl, itself is actually neutral because the one positive and the one negative balance each other, right? So the compound itself becomes neutral. All right, and these are all the websites that I had posted at the end of last week that I had told you about. You could go on and do some more practice. Okay, so we're going to move on to our final step with ionic compounds, right? And that's naming them. And we kind of hinted at this a little bit when we were doing that purple worksheet, how the anions were like chloride, oxide, hydride, they ended in ide. And here's how it gets to be that way. So the first step you're going to do is we know that these compounds form between a positive cation, our metal, and our negative anion, the nonmetal. All right, so when we're listing these, we always start with the metal first. It's kind of like how you would read it going across the periodic table. On the periodic table, all of these are our metals, and they're listed first. And then following them, you have your nonmetals. So just write in order as you would come across them at the periodic table. All right, so we're going to write the name of the positive ion first. So in this example, sodium. Then we're going to write the root name, or like the beginning part of that second ion. So the way I like to think about it is, okay, if the second ion, or our anion, is chlorine, we just want the chlor, okay? We're going to drop the ending of -ine. The chlorine goes to chlor. and then we're gonna add the ending of IDE, ide. And that's it. So it becomes sodium chloride. So if we just say sodium chlorine, I'm thinking you're still talking about sodium alone and chlorine alone. But once it becomes sodium chloride, that ide is like the hint that, okay, now it has become a compound. It has its own new chemical formula. It's a brand new thing. Okay, it's not just sodium and it's not just chlorine. It is sodium chloride, a new compound. Okay, so typically we don't include subscripts. We don't care that, you know, if it's a subscript of 2 or it's a subscript of 3 or 4. We don't need the subscripts in the name, except when the positive ion, that transition metal, might have a different number. And for us, we're not really going to worry too much about those. That gets a little bit more complicated, and we don't need to go into it that deep, you know, for an introduction into ionic naming and stuff. Cole, you good back there? Sure? Okay. All right. So, look at your periodic table. You're gonna have that out again. You just can't get rid of it. And so obviously the first one is kind of done for us because it's our example there. So it's dealing with sodium and chlorine. So it's gonna give us the chemical formula, and from the chemical formula, we should be able to now name the ionic compound. So my first element is sodium, so I just write sodium. My second element is chlorine, so I drop the ene and get chlor, and then do the final step of adding the ide. So our official name is sodium chloride. Just like we see in the example up here. All right, so let's go to the second example. Follow those steps. What does BE stand for? What's BE?
Beryllium.
Beryllium, very good. So you're gonna write the word beryllium. What's the O stand for? William?
Oxygen.
Good. So we are going to drop the ending of gin, right, and just have ox. What do we need to add to ox to name this? Ide. So you're going to end up with beryllium oxide. I thought that I had these written in there. I had the wrong screen, so I can't write on here. So you should have sodium chloride and beryllium oxide. All of them are going to end in ide. If they don't, you did something wrong. Okay, so the first element's always going to be your metal. Second one's always going to be your non-metal. The non-metal gets the ending dropped, and you add ide. That's it. Okay, we're going to go back and do some practice in a minute, but I want to finish a couple more slides so we can totally wrap up ionic bonds and compounds. And then we'll get a bunch more practice. So let's go to slide 17. This is kind of what a typical or very common ionic bond might look like if you have more than one sodium and more than one chlorine. Because let's face it, typically you're not going to just find one sodium and one chlorine. You're going to find a bunch of them together. But they're still always going to be in that 1-to-1 ratio. And we know that based on their subscripts. So it's going to form something called a crystal lattice structure. All it means is it kind of looks like these little squares in between them. Minus, plus, minus, plus, minus, plus. And it forms this nice, structured, very kind of cube-like structure, right? Think of a grain of salt, right? You can roll that around, one single grain of salt, you can roll that around. That's like a big version. It's a bunch of chlorines and a bunch of sodiums put together. But that's kind of like representing, if we broke it down and got it really small, at the smallest molecular level, that's what it would look like. It'd be making like these little cubes, okay? And so typically they're gonna be brittle solids, and it's the smallest part of the ratio that makes up the formula. So remember how we said, let's reduce that? So you might have Na50, Cl50, but that ratio reduces down to a 1:1 to just NaCl. Okay, so, and again, that's going to become more important as we get into our balancing chemical equations. It just makes our job easier. So we always reduce it down. So it could be Na 5 billion, Cl 5 billion. Still a 1:1 ratio, right? So whatever that ratio is from the subscripts, that stays put. But we can have a bunch of them as long as it fits into that original ratio. Okay, so you can see this is just kind of this three-dimensional view of what it looks like, forming these lattice-like structures, and it's all because of these opposite charges, right? They're holding them together and they're pulling equally, so you have this kind of nice set, predictable pattern. Good? Yes. You guys are pretty quiet today. All right, we're going to go back and go to some of the practice sites. Actually, let me do this real quick. The sites that are on our PowerPoint here, right here, I actually have just posted them. Oh, do this. Do it from over here real quick. There we go. I just posted them into Google Classroom. And so naming ionic compounds. And again, this is that same site that I explained to you the other day. And for me, I've already done it, so I can't like reenact it for you, but make sure when you click on, it might say that this connection is not private. Click the advanced tab, and then it says scroll down to the very bottom, and you'll see where it says proceed to chemicalformula.org, and it's going to be kind of grayed out and small. Once you click on it once, you shouldn't have to ever do it again. Like, since I've done it here, like, that's why I can't show you how it actually will look on your end. But we're going to go and actually start practicing some of these. So just, again, be careful. If it says it's private and you can't access it, follow those directions so you can actually get there.